Okay. Let's begin. Hopefully everybody's doing well and good and great and fantastic. All right, so today we're going to be talking about the area under the curve. Okay, so on Tuesday, I talked a little bit about sigma notation. And so that's going to be involved a lot going forward, at least when we're talking about the actual definition of what it means to look at the area underneath the curve. Okay, so a few announcements. There's homework due Monday night. It's over. Once we're done talking about what we've talked about today, you'll definitely be able to do all of it. Okay. And then don't forget about my office hours, Monday, Wednesday, Friday, 1 to 3 p.m. Okay. So there's also going to be another short quiz tomorrow that you're going to have to do by the end of the evening. I'm going to open it up after class today. You should have everything you need to be able to do that quiz. Okay, so make sure you get it done by Friday night. All right. So today we're going to learn how to approximate the area under a curve using familiar shapes like rectangles. We know the area of a rectangle. I don't know the area of some curvy thing, right? Or in general, if I'm looking at some function, I don't know how I could find the area, say, between x equals 0 and x equals whatever this number a is. Okay, so the point of the second half of calculus is to find out what is that area underneath that curve. That's sort of when you boil it all down, just like Calc 1, when you boil it all down, is all about finding that equation of the tangent line. When you boil this is really getting a little bit into Calc 2. I mean, it's always the end of Calc 1. But when you boil down integral calculus, all you're trying to do is find the area underneath the curve. Okay. So in order to do what we're about to do, we're going to need to know a few special sums. Okay. So the sums that we're going to need that are going to help us calculate a few areas, not all the areas. Later, we're going to learn a theorem that's going to make you just totally forget about what we're learning about today, and that's fine. But we're going to need these sums for today. Okay, so these sums are going to help us calculate the area underneath a few different polynomials. Okay, so I'm going to prove the first two. The second two, you can either trust me on those, or you can ask me later to show you a proof. The proof uses what's called mathematical induction. Has anyone ever heard of mathematical induction? If not, that's okay. But mathematical induction is something that you kind of need to be able to prove these other two sums. Okay. So let's look at, first of all, let's look at what these results say. So the first one says if I take the sum of a constant number n times, so the left-hand side here is really just saying this is c plus c plus c plus c, plus c, and there's n of those terms. Well, then the right-hand side, I mean, obviously, it's c times n, right? That one kind of proves itself. Okay. C has to be a constant number for that to be true. Notice that there's no I happening inside this sum. So there's no index that's telling me how to change to get my next term in the sum. All right. So I kind of already just proved the first result. Okay. The second result, well, what is the sum I equals 1 to n of I? If I wanted to start writing that sum out, what would that be? Hopefully everybody watched the video on Tuesday. Otherwise, you have no idea what these symbols mean. Oops. So the sum I equals 1 to n of I. Everybody watch the video on Tuesday? All right, well, we're starting at I equals 1, right? So this is, anytime you see a big sigma like that, that means it's going to be a big sum. And the bottom tells you where you should start I. So I is starting at 1. And then I write plus. And then I increase I by 1 every step, right? So I is equal to 1 plus, oops. Then I is equal to 2 plus. And I'm just putting 2 because that's what that term is. It's whatever I equals plus. So what's the next term going to be? 3.
I think we were all looking at the answer to that. Like,
Oh, gotcha. Yeah. But no, I'm going to prove that for you guys. Don't worry about that.
Like that's way. Yeah.
Okay, good. So yeah, you were adding all these numbers up to n. No, I'm going to show you how to get this. This is one of my favorite proofs ever, by the way. So this is what we're looking at on the left-hand side. 1 plus 2 plus 3 plus 4, all the way up to n, right? That's what this summation notation means. Okay, so we're going to show that this is equal to n times n plus 1 divided by 2. And this is, I'm going to go on a little bit of a tangent. There was a famous mathematician named Gauss. You might have heard of a Gaussian curve before. Gauss, when he was, I think, 8, proved this result. His math teacher came into the classroom and said to everybody, please find out what this sum is. His math teacher was really hungover, I think, and just wanted a few minutes to go take a nap while the students crunched out this sum. And so Gauss looked at that for a few seconds and said the sum is 5,050. And how did Gauss do that? Well, if we call this sum S, and this is how the general proof goes, okay? So I'm doing this for a specific n. I'm doing this for n equals 100 because, again, that's what Gauss's teacher tried to work his way out of, but this is going to work for any n, okay? So Gauss said, well, doing 1 plus 2 plus 3 plus 4 plus 5 plus 6 and on and on and on, that's annoying. I don't want to do that. So Gauss said, well, if S is equal to 1 plus 2 plus 3 plus 4 plus 5, blah, 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 all the way down, well, then S, I can add it in any order I want, right? S is also equal to 100 plus 99 plus 98 plus 97. 100 plus 99 plus 98 plus 97. All the way down to 1, right? So whatever the value of S is, that's what we're trying to find, right? Whatever it is, I can write that sum in either direction because addition is what we call commutative. Okay, so then this is the genius part. Gauss noticed, well, if I add these two things together, on the left-hand side, I'm just going to get 2 times the sum that I want, right? S plus S, that's 2S. On the right-hand side, we notice that 1 plus 100, what is that? 101. 101. Plus 2 plus 99, what is that? That's 101. Plus 3 plus 98, what is that? 101. And do you see that every single term now is going to be 101? Now, how many 101s do we have? Careful.
100.
We've got 100, right? Because for each term here, I've got a 101 down here, right?
101.
So I've got 100 times 101. Again, there's 100 101s. And there's still 2s on the left. And so that tells me that s is equal to 100 times 101 divided by 2. And so in this case, for n equals 100, well, 100 divided by 2, that's 50 times 101. And so little Gauss was exactly right. We get 50, 50, 5,050 for this sum. And he got it in a couple of seconds. Gauss was a very smart person, way smarter than me. So if we want to do this for a general n, well, nothing really changes. I just come up here and I change this 100. Now I'm going up to n, right? And I come down here, I change this 100 to n. The only thing that changes is now instead of 99, I'm just doing n minus 1. Instead of 98, I'm doing n minus 2. Instead of 97, I'm doing n minus 3, and so on. But you still get the same trick. But instead of 101, instead of getting 101, I'm going to get n plus 1 for every term. N plus 1 is n plus 1. N minus 1 plus 2, that's n plus 1. N minus 2 plus 3, that's n plus 1. And on and on and on we go. Okay. So then I can come down here and change 100 times 101. Well, now I'm working with a general n. I've got n plus 1, and there's n of them, right? So we have 2 times s is n times n plus 1. And so the proof for the general n is n times n plus 1 divided by 2. Okay. Any questions on that? Pretty fun proof, I think. Sadly, that doesn't work for the next two. The next two, again, there's a couple of ways that you can arrive at these that if you take my numerical analysis class in the future, if you're a math major, then it's not too hard to actually arrive at what these equal, but it is a little more difficult to actually prove that they work. Okay, so really quick with number 3, for number 3, I just want to write out the sum. So the sum I equals 1 to n of I squared. I just want to make sure we're all on the same page. What would this sum look like if I started to write out term by term? What would this sum look like? 1 squared, good. And then a plus.
2 squared.
And then 2 squared, very good. And then a plus. And we increase I by 1 and we get 3 squared. And then we'll do a plus and then one more. Oh yeah, plus 4 squared. Very good. And then this goes all the way up to n squared. So again, sigma notation is a really nice way of getting rid of the dot, dot, dot. Because sometimes you think it's clear what the pattern is, but it's not. So sigma notation really helps us to sort of tighten up all of this notation, okay? So, excellent question. Does I always start at 1? No, I always starts at whatever this bottom. With sigma notation, I have to tell you what I starts at, okay? If I had started at, say, 2, well, then this 1 squared wouldn't be here. We would start at 2 squared plus 3 squared plus 4 squared. Okay, so you always start I wherever you're told to start I. And you always end wherever you're told, oops, Oh, eraser, wherever you're told to end. Okay, and that won't always be n. Yes.
Does n have to be bigger than what I?
Oh, such a good question. Yeah, yeah, very good. N does have to be bigger than what I starts off as. So if you just have a n up top, where I'm assuming that n in this case is bigger than 2. Bigger than or equal to 2. Sorry, it could be equal to 2. And is it always? Yeah, yeah. And we're always increasing by 1. It's always integer value. Okay, and then number 4. So number 4, I equals 1 to n of I cubed. Well, again, this is 1 cubed. I'm starting at I equals 1, and I increase by 1 every time. I increase I by 1 every time. Oops, cubed. Okay. And I don't have what these are memorized, so don't feel bad about coming back to this page and looking up what these sums should be, because that's what I'm going to do later in the lecture, okay? So I don't expect you to have, the only one of these I expect you to have memorized, quote unquote, is the first one, because that one is sort of self-evident. The other ones, I will give those to if I expect you to use them on, say, an exam. Okay. All right, so let's use this. Let's evaluate the sum I equals 1 to n of I plus 1 over n squared. Okay, and we're going to do this for n equals 10, 100, 1,000, and 10,000. Okay, so notice in this sum, what's the only thing that's changing term by term when I start writing these out term by term?
I.
The n is not changing. I'm going to do this for a bunch of different n's. Is that broken? I'm going to do this for a bunch of different n's, but I is the only thing that's changing in each of these sums. So n, with respect to the sum, is constant. 1 over n squared is constant. So you could write this as 1 over n squared times the sum I equals 1 to n of I plus 1. Okay. When you have a constant in one of these sums, you can just pull it out in front of the sum. Then the other special thing that we're going to use, and these both of these just follow from, I mean, we've taken sums before, and you know these things implicitly if you're doing a sum of 2 things. And now we're just extending it to a sum of n things. Okay, so the other thing that we can notice is this is 1 over n squared times, well, if I'm doing the sum of I plus 1, I can do this as the sum of I from I equals 1 to n. Let me put this in double parentheses, plus the sum I equals 1 to n of 1. Okay, so you can break a sum apart into its individual pieces. As long as you're adding each piece. Okay. So we can evaluate this before plugging in any n's. We can actually simplify this pretty far before we actually plug anything in. Okay, so I'm going to get 1 over n squared times the sum I equals 1 to n of I. Again, this is that Gaussian sum that gives me that. Okay. N times n plus 1 divided by 2. Plus. And then what's the sum I equals 1 to n of just 1? If I were to write that out, I would write 1 and then I increase I, and then I write plus 1 and I increase I, and I write plus 1 I increase I do that n times, right? So what do I get when I do that? How many ones am I adding up here? Yeah, perfect. Yeah, it's just n times 1, and that gives me n. Very good. Very good. Yes, thank you, Safa. So then I can, there's a couple of things I can do. I'm going to get a common denominator in here. And so when I do that, I'm going to get the 1 over n squared. I'm still not touching that yet. I'm still simplifying inside the sum. Okay, so 1 over n squared times, well, this is going to be n squared plus n, and then plus, here I would get 2n over 2, right? So plus 2n divided by 2. Okay.
Where did that 2n come from?
So this was really n here to start. And to get a common denominator, I multiply top and bottom by 2. Okay. So simplifying a little further, this is 1 over n squared times n squared plus 3n divided by 2, right? And then if I want, I could factor out an n from the top. And then I would do that because that cancels with that. And so in the end, I'm left with n plus 3 divided by 2 times n. Come on, come on. There we go. 2 times n. Okay, I want to evaluate this now at a bunch of different n's. So when n equals 10, well, I'm going to get 13 over 20. When n is equal to, what's the other n's I wanted? When n is equal to 100, I'm going to get, well, 100 plus 3, that's 103, divided by 200. Right? Sorry, by the way, this is about point, so times 5, 50 plus point, this is not about, this is actually equal to 0.65. This is about equal to what, 10.3 times 5, 50.6, 0.506. When n is equal to 1,000, well, again, 1,000 plus 3 is 1,003. Divided by 2 times 1,000 gives me 2,000. This is really close to 0.5, right? If I round to 1 decimal place. And we'll go one more step. When n is equal to 10,000, this is 10,003 divided by 20,000, which is again very, very close to 0.5. So what am I doing here? Why am I doing this? We're kind of looking at what? N's getting bigger and bigger and bigger and bigger. So what are we kind of looking at? Yeah, indirectly I'm looking at the area and it's approaching 0.5. So when we're saying something approaches something, it's like a limit, exactly. This is exactly what I'm looking at is what is actually the limit as n approaches infinity, because this is what we're doing, right? As n gets bigger and bigger and bigger and bigger, well, that's all I'm describing is the limit as n goes to infinity. What is the limit as n goes to infinity of n plus 3 over 2n? We think it should be about 0.5, right? But what actually is it? when we look at this limit. I guess I shouldn't say but. What actually is that limit? Yeah, it's just 1/2 because this is a rational function where the degree of the top is 1. That equals the degree of the bottom, also 1. So I just divide those leading coefficients and I get 1/2. So this problem does come from looking at an area. We're going to see where exactly it came from in the coming slides. But yeah, this is exactly the idea behind the integral. And I'm going to draw exactly what's happening here in a minute so you can see how this actually comes from a sum or an area. Okay. Are there any questions about this? Okay. Why did n have an exponent of 1? Because it's just n. N is just into the first. Okay. All right, let's look at another sum. The sum I equals 1 to n of I squared over n cubed. All right, so again, when we're looking at these, we want to ask ourselves what's changing in this sum. So what's changing in here, or a better question is what isn't changing in the sum? Yeah, the 1 over n cubed, as far as the sum is concerned, is a constant. Okay, as far as the sum is concerned, the 1 over n cubed is just a constant, so I can pull it out in front of the sum, just like within a normal sum. If you have one thing times every term in a sum, you can just pull that factor out in front of the entire sum. That's all this is saying. Okay? So this is equal to 1 over n cubed times the sum, I equals 1 to n of I squared, right? So we want to find out what is the sum of 1 over n cubed times the sum I equals 1 to n of I squared. Well, this is 1 over n cubed times the sum I equals 1 to n of I squared. Well, that was in our theorem that we discussed, right? So the sum I equals 1 to n of I squared is n times n plus 1 times 2n plus 1 divided by 6. Again, I don't expect you to have that memorized. Look it up when you need it. Okay. All right, so this is going to be equal to then, this is equal to, well, now the rest is just algebra, right? It's going to be algebra, and then I'm going to take a limit. But this is 1 over n cubed times, well, n times n plus 1, that's n squared plus n. And then I'll do the next one separately. Now, n squared plus n times 2n plus 1. Well, you can FOIL this, right? So FOIL first, n squared times 2n gives me 2n cubed. Outside gives me plus n squared. Inside gives me plus 2n squared. And last gives me plus n. That's divided by 6. Very good. And so this is equal to, oh, I guess I thought I was going to write smaller. This is then equal to 2n cubed plus, well, I'm going to get n squared plus 2n squared is 3n squared. And then plus n just on its own. And then divided by, Well, 6n cubed, right? So whatever n is, that sum that we were just looking at is equal to this. Okay. If you want, you can factor an n out from the top and cancel that with one of the n's in the bottom. But really, the ultimate question was, what is the limit as n goes to infinity of that sum? Well, that's the same as the limit as n goes to infinity of 2n cubed plus 3n squared plus n divided by 6n cubed, right? And what is that?
1/3.
1/3, very good, because we get, again, a rational function where the degree of the top is equal to the degree of the bottom. And I'm looking at the limit as n goes to infinity. So I just divide the leading coefficients. I divide 2 by 6, which is just equal to 1/3. Okay. Questions on that? Again, this is the type of sum we're going to be looking at a lot in the next couple of days. All right. So an important thing that we're going to have to be able to do is go the other way. If I write out a sum, it's going to be very important for me to go, instead of taking sigma notation and turning that into a bunch of terms that I'm adding up, it's going to be important to go from a bunch of terms that I'm adding up to sigma notation. Okay, so I want to write 1 over n plus 2 over n plus 3 over n plus 4 over n plus 5 over n plus 6 over n. I want to write that as a sum. And we'll start I at 1 and we'll end it at something. But what's going to go inside of the sum here? Well, where does the sum start? It starts here, right? And the key thing to ask yourself when you're doing a problem like this, when you're converting a sum that's written out into sigma notation, the key thing to ask is, what is constant in each term? What is not changing in each term? And then what is changing in each term? So first of all, what is not changing in each term? What do all of these terms have in common? The 1 over n, right? So it's definitely going to be something over n. That's not changing. Every term has something over n. Okay, and then what is changing? The constant on top, right? So in the first term, we have that constant is 1. And then the next term, that constant has increased by 1, right? And in the next term, that numerator has increased by 1. And the next term, that numerator has increased by 1. That's exactly what we do with this sigma notation, right? So it looks like the top should just be I, if I is starting at 1. And then where should the sum end?
6.
6, very good. It's going to end, the last I that we have here is 6. So I is starting at 1, it's ending at 6. Okay. Now, this is not the only way you could have written this out. I prefer to start my sums at I equals 1. Some people prefer to start their sums with I equals 0. Well, if we start our sum at I equals 0, the thing that's not changing, the 1 over n, that's still not changing. It doesn't depend on I at all. We can just put that in there. But now what's the numerator going to be? When I equals 0, I want my first term to be 1. And then I'll increase I. Then when I is 1, I want my term to be 2. Then when I is 2, I want my term to be 3.
I plus 1.
I plus 1. Very good. And then what does the sum stop at?
7.
Careful. 5. Yeah, we want the last term to be the top to be 6. Well, that's when I is 5 in this case, right? So in writing a sum in sigma notation is not unique at all. You can write this. There are infinitely many ways I could write this just by starting the sum at different points, right? And I could start the sum anywhere, and I just need to shift the top appropriately. So most of the time, I'm going to start my sums at I equals 1. Okay, there will be rare cases where I might want to start my sum at I equals 0. These are really the only two cases you'll see me use if I'm converting a written out sum into sigma notation like this. Could I repeat the last part? So the reasoning for that, where we got that? Yeah, so this sum, again, you put in 1 over n. Oh, oops, sorry, guys. You put in 1 over n, because that's not changing at all. Okay, the thing that is changing is the top. And so if you start your sum at I equals 0, instead of I equals 1, and why would you start your sum at I equals 0 instead of I equals 1? Well, maybe you don't have a choice. Maybe I ask you to start your sum at I equals 0. Okay? There are many reasons you might start the sum at I equals 0 instead of I equals 1. Okay, but we're starting our sum at I equals 0. I want my first term to be 1. Well, that's I plus 1. Okay, then when I is 1, I want my term to be 2. That's also I plus 1. Okay, so you just need to fit the numerator to what's actually happening in each term. Each term is in the second sum is just the numerator is I plus 1. Okay, so that's where this sum comes from. So, and we stop at 5 because when I is 5, then I plus 1 is 6, and we want to stop at 6 over n. Okay. All right. So the whole idea behind finding the area under the graph of a function is to first find an approximate answer, just like we did with derivatives. So we're taking the reasoning we use for derivatives of can I find the slope of a tangent line? Well, at first the answer was no. I don't know how to find the slope of the tangent line, but I do know how to find the slope of a secant line. Okay, so the idea is to use what we know and then sort of force it to work by taking a limit. That's the whole idea. Okay, so we're going to do this by, instead of finding the area of some curved shape, we're just going to find the area of a bunch of rectangles and then add those up, because rectangles are easy to find the area of. Just length times width, right? Base times height, whatever you want to call those two sides of a rectangle. Well, there's 4 sides. You know what I mean. Okay, so we're going to approximate the area under a curve using a bunch of little rectangles. And then we're going to let the rectangles shrink smaller and smaller and smaller. Or you could think of it as, then we're going to let the number of rectangles get bigger and bigger and bigger and bigger. Okay. So what process is that a description of? I sort of already said it. Letting the width of the rectangles get smaller and smaller and smaller and smaller, and then looking at what we get. What is that as a description of?
The limit?
Yeah, that's a limit, right? That's a limit. So here's a picture of what's actually going to happen. So over here on the left, if I want to find the area under this curve, come on, there we go. If I want to find the area under this curve, I could use 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 rectangles. And then each of these rectangles, I could take their right edge to go up to the curve, right? They all have equal width. And then I could find the area of all these rectangles, add them up. That should give me a decent approximation. It's not going to be perfect. There's some overestimation there and there and there and there. And so the idea is, well, this isn't a perfect estimate, but if I let the rectangles shrink smaller and smaller, well, then that error that I'm seeing is going to get a lot smaller too. So the error is much smaller here, that overestimation. And so the idea is, well, let them shrink to 0. Or in other words, let the number of rectangles increase to infinity, right? Because I've used twice as many rectangles in the second picture as in the first picture. So that's the whole idea. Let the number of rectangles go to infinity, which forces, again, the width of the rectangles to go to 0. And in the end, we'll be left with the actual area under a curve, provided that the function that we're looking at is nice enough. Okay. So if we're trying to find the area under the graph of the function y equals f of x, above the x-axis and between the x values x equals a and x equals b, we're going to use in rectangles whose right edge goes up to the curve. Okay, so a picture of what's happening here. I know that's a lot of words. Give me a straight line, come on. A picture of what's happening. Okay, we've got some curve. And this is x equals a. This is x equals b. Okay, what we want to do is we want to approximate the area beneath the curve between x equals a and x equals b and above the x-axis to start. Later, we're going to talk about a generalized area, but right now, with a function that stays above the x-axis, I want to find this area. Okay, I want to find that area. And the idea is, well, I'm going to draw in rectangles. What is in? In's some number, some variable, right? So I'm going to start, I'm going to let the right edge go up to the curve. So there's my first rectangle. They're all going to be the same width. Now, do they all have to be the same width? No. Does it have to be the right edge going up to the function? No. But that's what we're going to do, okay? If you do it more generally, you get the same results. Okay. So then I'm going to draw my next rectangle. That goes up to this edge. Right edge goes up to the function. Then my next rectangle. Again, same width. That goes up to the function on the right side. There's my next rectangle. Here's my next rectangle. And here's my next rectangle. Here's my next rectangle. That's getting hard to say. So we do this. I'm going to draw some dots to say I do this some number of times. And then my last rectangle is right here. There's my last rectangle. Okay. There are n of these rectangles. Okay. So it seems like the things we need to know are the following. Well, I need to know what is this function height here at each of these points, because that gives me the height of the rectangle, right? If I want to find the areas here, I need the height of the rectangle, I need the width of the rectangle. So we'll start with the width. The width of the rectangles is fixed. I can find the width of the rectangles pretty easily. So how do I find the width of these rectangles? Well, I'm trying to fit in rectangles. Again, I'm using n of them in rectangles. I'm trying to fit n of these rectangles into this interval a to b. Well, how long is that interval? B minus a. So how wide should each of these rectangles be? Perfect. I'm trying to fit in rectangles into a length of b minus a. Well, I just into b minus a. That's b minus a over n, right? How many times does n go into b minus a? This gives me my width, which I'm going to call delta x. This is the width of each of these rectangles. Delta x. So fixed width, okay? So then I need to, the only other thing I need to know is the height of the function at each of those right endpoints, right? Well, if this is x equals, if this is x equals a, then what is this point here? The next point over. Perfect. The next point over is a plus delta x. So that means this point here is going to be f of a plus delta x. What's this going to be? F of, well, if this point here is a plus delta x, then how do I get this point here?
A plus 2 delta x?
Yeah, I just need to take another step of delta x, right? So that next function value is a plus 2 delta x. Okay, what do you think this one's going to be? This function height. Yeah, I'm looking at f at the x coordinate a plus 3 delta x. Okay, so and in general, if I take k steps away from x equals a, well, let's say this right endpoint here is xk. I'm going to call this point, this x coordinate, xk, which is, again, k steps away from a. So a plus k times delta x. Okay, that's that point there. Then the function value at that point is just going to be f of that x value, a plus k times delta x. Okay. Oh, do we have questions in the chat? Yes, thank you, Saba. So this general rectangle here, right here, is very good to look at, right? Then this is where we're going to pick up tomorrow. I don't have enough time to fully write out what we're going to have, but hopefully you can see where we're going to start building up the sum of these areas, right? Because what is the area just of this general rectangle here? Because this has a width of delta x, remember. So what is the area of that rectangle? Well, its height is f of a plus k times delta x. And its width is what? Delta x. So this is, again, once I've taken k steps away, this is the area of that rectangle that is k steps away. So the idea is going to be, well, I want the sum of all these areas. Let's add them up, okay? So now I'm using k as my index. Oops, sorry. Now I'm using k as my index. This is what's going to be a very, very, very special interest to us, okay? This is what's going to give us, when we take a limit, the actual area under a curve, okay? Do we have any questions? I used k. You can use I if you want. I don't want to use n because in the sum here, because I'm using n as the number of rectangles. So I want the thing that's changing. The thing that's changing is I, right? Or k rather. I'm taking the thing that's changing is how many steps away I'm taking to find that rectangle, and so that's why I'm using k instead of n. You can use I instead of k if you want, but that's just a personal choice. Okay. All right, so if we don't have any other questions, please wipe down your desks as you go, and I'll see everybody tomorrow.
Thank you.
Thank you.
Thank you.